Thermal resistance is measured between 2 points with heat flow. Heat flow causes the source point to increase in temperature with respect to a sink, such as room air. In thermal systems, power is analogous to current, and temperature is analogous to voltage. Thermal resistance is referred to as theta with the hot and cold reference points. The thermal resistance from the die junction to the ambient air temperature is theta JA. The units are degrees Celsius per watt. Knowing the thermal resistance value helps to calculate the die temperature at a given power dissipation. The manufacturer specifies the thermal resistance of their products. Measuring thermal resistance teaches you about the technique. Silicon die can function at very hot temperatures. Plastic encapsulation, solders, and conductive adhesives usually limit the maximum die temperature. Maximum die operating temperature is typically 125 C, although some are much higher. To find theta junction to ambient, measure the change in die temperature with respect to the ambient air temperature. Measure the power the die is dissipating. Silicon junction diodes have a well-known temperature coefficient of about -2 millivolts per degree C. Let's test a 1N914 diode model using LT Spice. The diode is biased at about 0.9 milliamps to keep self-heating low. To measure thermal resistance, the diode must heat up. Current is increased in pulses using an NPN emitter follower. The current increases to about 100 milliamps, heating the diode. It is turned off for a short period, and the diode voltage can be measured to obtain the temperature of the die. Simulation shows the current pulsing from 102 milliamps down to 0.9 milliamps. The diode voltage is 851 millivolts. At high current, where the diode heating is at 87 milliwatts. When the current drops to 0.9 milliamps, the temperature is measured. This voltage is 580 millivolts. It is the reference cold voltage before the die heats up. The circuit uses +5 volts DC from the Pico. It is important to double-check wiring and component orientation. Miswiring can place 5 volts on one of the I/O pins, and the Pico will be damaged. Insert the Pico into the breadboard. Add a jumper wire from Pico pin 38 to the minus bus. Add a jumper wire from Pico pin 34 to the minus bus. Add a jumper wire from Pico pin 33 to the minus bus. Add a jumper wire from Pico pin 28 to the minus bus. Add a jumper wire from Pico pin 23 to the minus bus. Add a jumper wire from Pico pin 35 to the plus bus. Add a 0.1 microfarad capacitor between the minus bus and the plus bus. Add a 3K resistor between the plus bus and breadboard bus 6A. All component leads are kept a full length. Trim the ends if there is adhesive from a tape strip. Connect the diode from breadboard bus 6C to the negative bus. Add a 2-inch jumper wire from breadboard bus 6E to bus 2D. This wire is used as a thermal isolator from the 15 ohm resistor. Add a 15 ohm resistor from breadboard bus 2E to bus 1F. Insert the 2N2222 transistor into the breadboard. Note the flat side points up into the photo. The emitter connects to bus 1G, the base to bus 2G, and the collector to bus 3G. Insert a 120 ohm resistor from the transistor base at bus 2H to bus 6H. Add a jumper wire from bus pin 6J to Pico pin 20. Add a jumper wire from the transistor collector at bus 3J to the bottom plus bus. Note that the two plus buses are not connected together. The top bus is 3.3 volts and the bottom one 5 volts. Add a jumper wire from Pico pin 40 to the bottom plus bus. Add a jumper wire from Pico pin 31 to the 1N914 anode at bus 6D. Add a jumper wire from Pico pin 32 to the 2N2222 emitter at bus 1J. The heating temperature measurement algorithm is simple. Power is turned on and off. During the longer on cycle, power is measured. During the short off cycle, temperature is measured. Returned analog converter values are variables A0 and A1. Putting it together, we simply add a couple of loops to save data during the heating and cooling cycles. The thermal resistance is calculated from the power and temperature data. The thermal time constant is calculated from the cooling temperature data. The program code is available on GitHub in the Thermal Tester Pico folder. You can also drag and drop the UF2 file into the Pico boot drive. We will go through the code for the educational aspect, where you can enter, then save, and compile the code. Two long variables are used to accumulate ADC averages. The float arrays store diode power in milliwatts and then change in temperature in Celsius degree. The T variable is used for loop timing. Pin 15 controls the power on-off circuit. Although the baud rate is set for 460/800, the data is sent at maximum speed and most settings work. The ADC is set for 4096 levels at 12 bits. Analog channel A0 is averaged for 64 readings. This is the temperature measurement value, which has a resolution of about 0.8 millivolts. Channel A1 is averaged for 8 readings. It is used to calculate power, and a higher noise is tolerable. Global variable analog AVG contains the A0 value, and analog AVG2 contains the A1 value. The first function of the main loop is to wait to start. Reception of a lowercase r begins the test. Header text for power and temperature allow the plotter to designate the plotted values. The heating cycle causes a bias in the measurement, and two different zero references are needed. An initial cold diode temperature is recorded in Ref 2. Ref holds the initial heating cycle start. The heating cycle is a loop of 95 millisecond power on, 5 millisecond delay, then reading the temperature. The zero starting point is subtracted from the temperature to generate the delta. The subtraction is reversed to correct for the negative slope. The cooling cycle is the same as the heating cycle, except no power is applied. The initial cold temperature Ref2 is used to calculate the delta. With no power applied, the measurement bias is not present. Finally, power readings are averaged and compensated for the 95% duty cycle. The thermal time constant is measured by locating the cooling delta that has dropped to 63% of the full charge. Save your code, then compile and upload it to the Pico. Start the serial plotter under Tools. Send an R character to start the test. The diode will start heating. The power in milliwatts is shown in the blue plot, and the delta temperature in degrees Celsius is shown in the red plot. The heating cycle runs for 50 seconds to ensure the die temperature stabilizes. After the heating cycle, the exponential cooling is recorded. Diode heating and cooling is influenced by air currents. Even breathing on the diode can change its temperature. Testing the program and observing the diode voltage shows power on and off cycles. Note the small recovery of the off cycle. This recovery was also observed using only resistors instead of the diode. It is believed to be a recovery of Pico electronics after the large voltage step.